This video introduces you to the basics of building models to make predictions about your data. Now, in order to give you the ability to get some data and make some mistakes with the data and have a reasonably controlled experience, we've built a data generator for you specific to this course. Thank Professor Dietz for making it. It runs on her website, so you can go to her website and get a fresh set of data just for you. In order to give a little bit of traceability, you type in your AUID into this box. If you feel uncomfortable about doing that, you can type something else. So you can say something like this as well, and then hit the submit button. It goes and churns. It gives you just a text page, which then you can select all, and then say save as, or just actually copy, and then paste that into a text file named something or other, probably your AUID, .csv. Once you've saved that file, that's the file you'll load into R. At this point, you should not be looking at the details of the data very much, although you can notice that it has 5 columns, a group column, an X, a Y, a T, and an S column. The group column is categorical. The X and Y are definitely numerical, and the T and S look either numerical or perhaps they are simply Boolean, true or false, a 0 or a 1. And in fact, that is true. So that's enough to get started with for the moment. So save that text file somewhere. You can find it and name it something or other .csv. Okay, so once you've saved the file, then bring it over into R. How do you do that? Well, we're going to end up, first of all, clearing out your environment. My environment's already clear, so I don't have to do anything. We're going to load 2 libraries, the tidyverse library and the modelr library, which is convenient for doing models and predictions. Okay, once you've got those libraries loaded, it's time to bring in the data. I'll call it raw data. You can use the read CSV function, as we've been using already. There's my CSV file. I called it stat312 ml Michael R, but you can call it whatever you like. Don't forget to upload your file to Canvas, please, because if you don't, then I can't verify that you've done it correctly. Okay. Takes just a moment to load it in. You can see there's 1,000 observations, or rather 10,000 observations of those 5 variables: the group, the X, the Y, the Z, the T, and the S. And you can see all of that came in just fine. At this stage, we don't want to touch the data. We don't want to look at it. We don't want to bias our understanding of what's in the data. So what we're going to do is we're going to follow Hadley Wickham's advice from R for Data Science, his book, wherein he says that you should split your data randomly into 3 different samples. The first sample is called the training sample, and that should be about 60% of your data. The second should be the query set of the data, which should be about 20%. And the final set, also 20%, is the testing data. You use each of these a little bit differently, and the point here is that you're simulating the process of peer review of your model. But you are doing all the steps. And to that end, the training data, you can do anything you want with it. Explore it, look at it, plot it, make models, try to optimize your models, whatever you want. The query data, you are able to use to verify which of your models is doing the best. But you're not allowed to do anything automated, or at least so Hadley says. My suggestion is that you interpret it as what he's saying as the following. Instead of doing something manual or not, you should use this only for the process of selecting which model you're going to mark as this is my actual model. So what that means is you're not allowed to modify the models based on what you've seen with the query data, but you're allowed to look at the output of the models. Finally, once you've selected the model you want to use, then you run your selected model, one of them, on the test data exactly once, and that is the data that you will report the performance of your model from. You're not allowed to modify your model or tweak anything again and rerun the test data. Should something go wrong, you get crummy results, well, you get what you get. And if you decide that you've made an error and you want to change your model at that point, you need to go get a fresh set of data. Now, in practice, there can be a real problem. But for the purposes of this particular assignment, you just go back to the website and get yourself a fresh set of data. That's why we've made it that way. Okay, so how do you do the split? Well, you want to randomly pick 60% of these 10,000 rows and pop them into the training set, and the other 20% from that training set, from that data set as well. How do you do that? Well, R can certainly produce for you a sampling frame that's pretty convenient. The way I think the best, there's various ways you could do this. I think the simplest way is simply to randomly assign a number from 0 to 1 for each of the rows of that particular data set. And then if that number is between 0 and 1 and they're unique, then you can say, well, give me the 60th percentile of that number as your training set, for instance. Okay, so let's do that. So let's make that sampling frame. It's going to take the raw data, and we're going to add to it what I'll call snum, which is my sample number that I'm going to use between 0 and 1. A way to do this to ensure without replacement, i.e. unique numbers, is to use the sample int function. That's what this is for. It's to help you build sampling frames. And the sample int function takes two inputs. The first input is n, i.e. the number of rows. The second is also n. It's telling you how many different things you're going to do, how many different samples you're going to pick. Permutations and combinations kind of notation. All right, and we want to normalize it between 0 and 1. Okay, now you'll notice I've got now 6 variables in my sampling frame. Okay, I'm not looking at the data, but I know that it has a new column called snum. So now to pull out my training data, it's actually very easy to get my training data. I just say I want to filter out all the snums that are less than 0.6. And once I've done that, I have no need of that snum formula anymore. Snum column anymore, so I will just delete it altogether. Oops, and I wanted to call that training, not trainings. Okay. Get rid of that training data. Well, whatever. Okay. Similarly, I get my query set by building an appropriate filter. The filter's got to be, instead of less than 0.6, it's got to be greater than or equal to 0.6 and less than 0.8. That's my query set. And finally, my test set is snum greater than 0.8. There we go. Okay. Now, once you've got these 3 data sets, it is convenient for you to save them somewhere safe. In particular, I would like you, for your Canvas submission, to submit each of these 3 files. If you fail to do this, you will have to rerun the exercise from the start. So, warning, you need to save your data and upload it. So how do you do that? Well, let's take our training set and just pipe it into write CSV. So you can say something like Michael R. training.csv. That now makes a CSV file. It's saved on my computer. I can upload that to Canvas. Similarly for the others. Name them something obvious so that when I go to grade, I will know what you mean. Okay. All right. Now, that's the end of the sampling phase of the project. I now forget about the query and training sets for a while. You can do anything you want to the training data. So, for instance, you could just literally put your eyes on it and look at it and say, okay, here's the training data. I see that indeed there are a bunch of different values for the group. I see there's a bunch of numerical values for the X and Y and the T and S. You could do whatever you want with it. So for instance, you can scatter plot it. You could do something like, let's say, let's go ahead and scatter plot this. and color by group, for instance. There you go. And you can see that the groups are definitely kind of different. Notice that green group, group B, is kind of a little different from the rest. That looks kind of interesting. So let's peel that guy out. And maybe we'll color by T or something. Okay, well, that looks kind of interesting. It's got some interesting little curvy behavior to it. Certainly, plotting is good, but also so are tables. So certainly go ahead and make a table. Say, all right, looks like the groups are kind of evenly distributed. What about if I've got a T? Okay, there's some interesting behavior there. This table's maybe a little bit better if I pivot it. I don't know. All right, so definitely looks like T has something to do with the number of rows from each of these groups. You can go explore however you like. There's clearly something going on here, and there's a variety of things that you can explore. Your goal in this project is to come up with some of the variables that you'd like to use as explanatory variables and others that you'd like to use as response variables. Which should you pick? Well, that's actually up to you, in the sense that I want the variables to be actually kind of reasonable, that those are ones you're going to try, and I'll have a look at that when I go to grade and give you some advice on that. But hey, take your pick. And the point is that this is to teach you the process of doing the modeling. If at the very end you go run your gold standard model that you've made on the test data and it's a disaster, I actually don't care, and you will not lose points for that. It's totally fine. I want you to follow the process and demonstrate that and really understand how the process works. So if the results aren't too good, that's okay. That's not what we're after. If you feel bad about that, well, fine. You're welcome to get another data set and try again. That's okay. But I want you to run the process correctly. Okay, now, at this point here, I can kind of see that there's something going on with Group B. So let's move from the exploration phase to the model generation phase. Still working with the training set. Let me peel out and say, you know what? I'm just interested in Group B. Notate that information in a comment in your R script file. Write it down and say, hey, professor, I'm going to study the behavior of this particular variable given the behavior of these various other explanatory variables. Do you use a little terminology? You have the response variable, which in this case is going to be the x and y. In particular, I'm going to be interested in the y, is the response variable. And the explanatory variables are going to be the group. I'm going to select group B, and the x is also going to be an explanatory variable. So I'll have a quantitative and a categorical explanatory variable. Quantitative explanatory variable, that's x, and a categorical explanatory variable, that's the group, and I'm only going to be focused on the group B for this video. If you look in the instructions carefully, you will see that I'm asking you to try a bunch of different models for a bunch of different tasks. Please follow those instructions carefully. Okay, so let's filter out the training data for just group B. So I'll call it training B. And there's just group B. Okay. Now we're still allowed to play with this training data any way we like. So for instance, I can go ahead and do the plot that I just did, make sure that I haven't messed anything up. For instance. And yes, looks the same. Good, I didn't mess it up. Okay. What possible models to say, this kind of looks linear-ish. I mean, there's definitely a linear-ish trend. There's some substantial correlation going on there. So I can make a linear fit. And I can propose to R that this is y is governed by x. i.e. y is determined by x, y versus x, using the training B data. Okay, R happily fits that. Now, what do I do at this point? Well, I've got my model, or at least I have one model, that linear fit. I'd like to add in the predictions. If I look at the training B data, what I'd like to do is I'd like to add another column of predictions from my linear fit model. Okay, and that way I can see how well the x values are predicting the y values based on this particular model. Certainly I could drop in another column with mutate, but the modelr library that we put in at the very beginning here, that modelr library actually supplies a bunch of useful convenience functions that know how to unpack various kinds of models and run them for you. So it's kind of convenient. Let's call it training lfit. And what you say is you say add predictions, and then you tell it what model you want to use. And you can just drop in the linear fit outright, give it a name, and here it is. And you can see there's the x value, the y value. Now these are the lfit y values. You can see they do seem to track pretty well. Certainly you can go ahead and plot them. So let me pull up my previous plot command, and I'm going to actually peel out this aesthetic and pop it onto here and add another aesthetic for my lfit. You might be saying, hey, I could do this a different way. Oops, except for the fact that I can't spell. I need the training lfit object. There we go. You're certainly right if you say, hey, I could do this some other way. True. You are not wrong. However, this way is convenient because it will work for the second model we want to play with next. And it's the same exact syntax, which is a little bit more convenient than, say, using an AV line, for instance. Okay, great. So what about if you said, well, I'm wondering how good of a model this is. You can see it deviates a little bit around the ends, a little bit over here and a lot of it over here. You can take a look at the residuals, and that might be kind of useful too. How do I do that? Well, the modelr library provides not just predictions, but also provides residuals. The residuals are telling you the difference between your proposed model, this lfit column, and the actual response variable you're aiming for. I'll tell you the difference. Those are called the residuals. Oops, and I just screwed that up. Hold on. Okay, fixed. Okay. And so you can see the residuals are kind of small, but they vary. And of course, this being what it is, we can go plot it. So for instance, I could plot the x versus the residual. Oops. And you can see there's some interesting structure there. The residual appears to kind of have a little bit of a hump shape. This suggests that maybe I might want to use a different kind of model. Okay, well, hey, what kind of models are out there? There are huge numbers of models. One of the simplest ones you might try is a low-order polynomial. Something like y equals ax squared plus bx plus c, rather than y equals bx plus c. Got that ax squared term in there. Okay, well, R knows how to deal with that and actually can give you that polynomial fit using the lm function as well. How? Well, you say y versus, instead of x, you say poly x, comma, and then the degree of the polynomial. If you want x squared, you put a 2. You want x to the 15, you put a 15. Hint, don't put x to the 15 because it probably won't work so well. There are some deep mathematical reasons why this is not a good plan. All right, regardless, here we go. But there's our polynomial fit. How do you add in the residuals and whatnot? Well, it's actually exactly the same command we had before. Just swap out the lfit for the polyfit. And make sure you get all of them. There should be 4 of them. Okay. Of course, I named this something stupid, but call it both maybe. Okay. Now we can take a look at those residuals. Actually, this is just the polyfit. My bad. All right, whatever. It's called training both, and we'll just have to deal with it. Okay. In any case, let's plot those residuals. And, well, there's a little bit of a dependence, a little bit of a correlation, but it's a lot less than it was before. Okay, great. Well, now we're in a situation here where we're about ready to make a choice between the polynomial and the linear fit. I think the polynomial is better, honestly, but we've been messing with this training data. We now want to run against a set of data we haven't seen before so that we can do an actual fair comparison between these two models. Great. So how do we do it? Well, we can do it all in one go with the query data. This is now the time to unpack the query data. Remember, we're not allowed to change our models once we've seen the query data, but we can choose between models. So here we go. Let's take our query data. We'll call it query B. We take our query data. We filter out the group. And now, what are we going to do? Well, we can use the same model. We can add our predictions, lfit, same model as before. It knows how to use the new data. This is one of the benefits of using this modelr library. I'll call it the same thing, though, lfit y, or lfit, say lfit pred for predictions. I can add the residuals from lfit, and I'll call it var equals lfit resid. And you know, I can just keep going. Let's add predictions from the polyfit. And call this var equals polyfit fit pred, and add residuals. Polyfit var equals polyfit resid. Okay, I think I got everything. Let me check to make sure. All right, we've got the query data we're using now for the first time. We've got the group. We've got the predictions. There's the lfit and its predictions. We've got residuals, lfit residuals. We've got the predictions, polyfit predictions, and residuals, polyfit residuals. Looks good. What did I do wrong? Unexpected. Oops. Somehow or another, I got a quote problem. That explains why I had. Okay. There we go. Okay. All right. It's done the deed, and now we can just go take a look at the data. In fact, it's kind of convenient. In this case, you could use the residuals to make your determination. However, I think it's actually pretty clear right from the plot which one we want to pick. So let's plot the original data. Let's plot polyfit predictions. Call that one red. And lfit predictions, and we'll call that, and I see I missed the word color here. Okay, and I can't spell geom apparently. And there we go. We got the red polynomial fit, and we got the blue linear fit. The polynomial fit sure looks better to me by eye. This is what Wickham suggests you do by hand, i.e. manually, is look at it and make your decision. Okay, I am choosing the polynomial fit to go for my test data. All right, cool. Well, now we crack up in the test data. We use the test data exactly once. How do we do it? Well, we're going to do it just the same way we did as the query data. Oops. Just the same that we did as the query data, but now with the test data. We only use the one model we are choosing. So we are just choosing the polyfit. We get to do this once, and now we get to look at it. Now, the way to go to look at this, you can certainly do a plot like I've got up on the screen. However, I think actually what's a bit more useful, seeing as this is the final product, is just to take a look at those residuals and make a histogram of them. And there you go. That's the final result of this particular process. Well, it doesn't do bad. On the other hand, the point is this is now a fair test because we've never seen this data before. We know this is a random sample from our original data. And so this is how you do the modeling and prediction process if you're just one person. Certainly if you have some peers, you can do a peer review process, and that helps. That gives you an additional layer of protection against making mistakes or adding extra biases. But if you run this process yourself, this is actually a pretty good way to ensure that you're not fooling yourself. Because human biases can end up getting folded into the data very easily. If you say, oh, you know what, let me just make it a little tweak. Oh, let me run it again. Each one of those times, you've added a new variable. The new variable is how many times should you resample the data before you pick it, before you have the final answer. And then you're starting to introduce some small sample bias into that particular new variable, i.e. the number of times you're doing the sample. And that can screw up your results. So, with that, I hope this was informative and useful, and I hope you enjoyed it.